This is Dr. Lewis going over some material which will typical of the questions that will be in the assessment, which replaces the written exam. Just to remind you that my lecture course was rewritten, so certain topics such as VSEPR, which you've seen in previous past papers, and molecular orbitals of molecules like nitrogen, oxygen and dicarbon will not be in this exam, so they were not in my lecture course. So what I did do was concentrate more time on organic chemistry. And the last section was on reaction mechanisms, and this particular question is based on L4, that lecture file in Canvas, which is called Organic Reaction Mechanisms. So we looked at the substitution reaction, which is where we swap one group for another, and you can see here in this case we've swapped Br for OH. There's two mechanisms possible, one called SN2, which is on another YouTube video, and this one which is called SN1. So obviously look at the lecture notes for the background of this. I've just summarised the key bits to think about because it says draw a curly arrow mechanism for the reaction below. You're just given the equation, but you're not given what sort of mechanism it is. So you've got to decide which mechanism it is. You've got to write the rate equation, and you've done kinetics with Dr. Horozov, and explain your choice. So the most important thing to distinguish between SN2 and SN1 is the structure of the organic electrophile, that's the organic substrate. If it's primary, it can only undergo SN2, and if it's tertiary, which in this case that's the reactive centre there, it can only undergo SN1. Now what I haven't done is go through secondary carbons, because that is always a bit more tricky. It also depends on the detail of the structure, the solvent, the leaving group, the nucleophile, etc. So that would make things rather complicated. So I've stuck to the two extremes. SN2 must be primary and SN1 must be tertiary. So this is a tertiary carbon. And that means it must undergo an SN1. So SN1 stands for first order kinetics. That means it's a unimolecular process which just starts with this one dissociating, and it does that because it kicks off bromine as bromide, and it leaves behind a carbocation. And because it's tertiary carbon, the carbocation is stabilized by the inductive effect. It's also helped by having a good leaving group, and bromide is a good leaving group, and the carbon-bromide bond is relatively long, it's relatively weak, and because it's polarizable, the solvent, if it's a polar solvent, helps to polarize it and is more likely for the bromide to come off. SN2 cannot happen for this tertiary system because remember the transition state involves 5 things attached to that carbon at the same time, and because there's 3 carbons already attached, the steric crowding would be such that the height of the energy barrier, what we call the activation energy barrier, is just too high for it to occur. But it does go very fast via the stable carbocation. So we're going to do the mechanism now. So that's an equation, not a mechanism, and we're going to use curly arrows, which is a vital part of you understanding organic chemistry, is to get the hang of curly arrows. So it's a unimolecular process, which means it doesn't involve anything else but this molecule, and it simply dissociates like that. So the curly arrows say that the electrons in that bond break and go on to create bromide and leave behind a vacant site here. So that will end up positive and that will end up negative. So this is what we call the rate determining step. It's the bottleneck, if you like, in the mechanism, and it's why the kinetics is first order, because it's entirely dependent on the speed of this step. So we're going to generate a carbocation there, and bromide has come off. Then the nucleophile, so that's the electrophile. The nucleophile is water. Now water is not a very good nucleophile, but because it will be in large excess, and also because the carbocation is very reactive, it will very rapidly, so this will be a very fast step, will quench that carbocation. So this is not important. This is not important in the kinetics because it's the first step, which is the slow step. Now the initially formed intermediate has still got two H's attached to it, so it's not quite the product yet. But a very fast equilibrium process, more water can act as a base and just simply take that proton off. So that's taking the proton off, and that bond breaks, and then it goes on, that pair of electrons goes on to the oxygen, and that gives the product. So the key part is the first step, and we're going to get H3O plus as a byproduct, and we've also got Br minus, obviously. So that's the key step, that's the rate determining step, and in lots of SN2 processes there'll only be one step following, a fast step, but in this case we've got an extra step just to remove that proton to give us the product. Okay, so that's the curly arrow mechanism, and then it says write the rate equation. So the rate equation is always the rate equals some proportionality constant called the rate constant, and in this case it only depends on one thing. It's unimolecular, so it only depends on the concentration of, and we'll just call it RBR, right? The alkyl halide. So that's all it is, that's the rate equation. And what favours SN1? In this case, SN1 favoured by tertiary carbon giving a stable carbocation. Now, it doesn't mention anything about the solvents. It doesn't. The nucleophile is a weak nucleophile, so those two factors are not really involved in this favouring an SN1. So the only other bit that favours it is the carbon-bromine bond. So carbon-bromine bond is highly polarizable. It's a long bond, relatively weak, and Br minus is a good leaving group. That essentially means Br minus is a nice stable anion, so it's happy to come off and exist without reacting with something. So that's SN1.